All right, guys, so what we're going to be talking about here is we're going to be talking about something that is called the mean value theorem. Now, the mean value theorem is something that's very important to a lot of things in calculus, even though the idea behind it might not seem overly difficult. And so just know that this is something that is very important because it's the basis of a lot of things we talk about, especially second trimester. But it's an underlying thing, not something that you absolutely have to know in order to succeed second try in what we talk about. Okay? So, as a quick reminder, when we talked about average velocity, we said that we use the formula to find average velocity in any given situation with something that is moving, and we have a formula that determines the position of that particular object. We use this formula, S of B minus F of A, S of A, all over B minus A. Now that might not look really familiar, but if we say that S of T is our position function, and A and B are our start time and our end times for the time interval that we are interested in, then what we really said, and we talked about this before, was that the formula for average velocity is just saying displacement, which is how far you are from where you started, divided by time elapsed, which is how long it took for us to get from point A to point B. Okay? That is our formula for average velocity. So let's say you were decided you're going to go and visit your grandma that lives in California, leaving from Brigham City to get some special brownies. You love her brownies, you're headed down there to California to get some because she makes them awesome. Okay, and so you want to drive down there just to get some brownies. So as you leave Brigham City, you pass directly in front of an officer on Main Street. Okay, now, the officer doesn't see you doing anything wrong. You're just on Main Street. You drive by him at 4 p.m., but he doesn't say anything, does nothing to you, because you weren't breaking any laws. You were going the speed limit on Main Street, not that big of a deal. So what happens is you head down I-15 for about 4 hours, and after those 4 hours, you arrive in Las Vegas. Now, first of all, I do realize that that is ludicrous. First of all, Vegas is 480 miles away, but there's no way you're really getting there in 4 hours. But for the sake of this story problem, let's say that you somehow are able to do that. Now, I know a lot of you right now are saying, okay, I got to Vegas. That means that my average speed, okay, again, which we talked about before, is just displacement, that's 480 miles, divided by how long it took would be 120 miles per hour. That is really fast to be driving that fast all the way down there, okay? Now, here's an issue. The cop in Brigham City that we saw, he had a friend in Vegas, and although he did not pull you over, he said, you know what, they're looking again, I know this is really contrived, but he said, it looks like they're headed to Vegas, keep an eye out for them because they look a little shady, okay? So he writes down his plate number, sends it to his friend, and 4 hours later, the cop sees you, as he's like, okay, I'll be on the lookout for them. He sees you, but you understand that if you're in front of a cop, you can't be speeding. So you slow down to 65 miles an hour, exactly 4 hours from when the first cop saw you. So about 8 o'clock, you're pulling into Vegas, and this cop sees you, and he pulls you over. And he says, you know what? I am giving you a ticket. I'm giving you a ticket for going 120 miles per hour, even though I did not see you doing that. Now, you're like, okay, well, that's not fair. You didn't see me doing it. There's no way if you didn't see me going 120 that you can give me a ticket for going 120. Now, this is actually not to this extent, like they wouldn't be that far apart, but the police officers, highway patrolmen, they actually do this from time to time. And here's why he was able to give you a ticket for going 120, even though he didn't see you speeding. If your average speed was 120 miles per hour, that meant sometimes, like let's say, here's kind of a graph of velocity, and 120 miles an hour looks like that. Now, obviously, when you were driving, you weren't just going 120 the entire time. Like when you were in front of the officer in Brigham City, you weren't breaking the speed limit, so you were going 25 there. And when you were close to Vegas, you were going 65 miles an hour and the cop pulled you over. So obviously you weren't going 120 miles per hour. Chances are you did something like this. You sped up and then you kind of you went forward. And then as you got to Vegas, maybe you slowed down. Maybe there's some traffic somewhere along the line, so you went back and forth over 120 miles per hour. But here's the point. The officer was able to give you a ticket for going 120 because if you average 120 miles per hour, there had to be somewhere along the trip that you were going exactly 120 miles per hour. Notice he didn't give you a ticket for going 130 or 140, even though chances are that's probably how fast you were going somewhere along the line. He just knew that if your average speed was 120, then that means that your instantaneous speed somewhere along the line had to be 120 miles per hour as well, even if you were only going that for a split second. Now, what that is saying, that is what is known as the mean value theorem. And the way that we look at the mean value theorem in this class is not like a story problem like we just looked at it there, although it does happen from time to time. But for the most part, what we like to look at instead is we like to look at it applying to functions. So what I'm going to do here is we're going to talk just real briefly about this mean value theorem and how it applies to functions, and then we'll kind of tie that together with that analogy we used at the first of this talk. In order for us to use the mean value theorem on a function, a couple of things first of all must be true. Number one, the function must be continuous and differentiable between the two x values that we are interested in. We'll always be looking at some sort of interval of x values, and as long as the function is continuous, which means I don't have to lift my pencil, and differentiable, which means there are no corners or cusps on that interval we're looking at, then we can use this formula right here. Okay, and I know this doesn't make a ton of sense right now. We're going to look at an example here in just a second to help us understand what's going on with the mean value theorem. The mean value theorem says this. It says that if I find the slope between the 2 points that start and end my interval in question, if I find that slope, and that is the slope of a secant line, because we talked about that before, the slope of that secant line must somewhere along the line, and we don't know where that is just yet, but somewhere along the line, the derivative must give us the same slope as the secant line. Another way to look at that is saying that the average rate of change, the slope of the secant line, must equal the instantaneous rate of change, which is the derivative, somewhere, and we're going to try and figure out where that is. Okay? So again, in order for us to use this, the function has to be continuous and differentiable. No corners, no cusps, and there cannot be any sort of discontinuity. Only on that interval, okay? If I'm looking at a function, and we'll look at this more in just a second, but I have like a cusp right there, and then the rest of the graph is just fine, I can still use the mean value theorem between those 2 points. I just can't use it if this x value is included. We'll talk more about that in just a second. Okay? So, here's what's happening. And that last slide I skipped it because we'd already talked about it. Here's what's happening. I've got this function y equals x squared minus 5, and I'm interested in how the mean value theorem applies on the interval from -1 to +3. Well, if I were to look at this function at x equals -1, I can see the point -1, 4 is on the graph. And if I was looking at x equals 3, I can see the point 3, 4 is, or 1, -4, -1, -4, excuse me. And then the point 3, 4 is also on the graph. Now, here's what the mean value theorem is saying. Okay, it is saying that if I find the slope, and that's a really bad secant line that I just drew, but pretend I connect those 2 points together, if I find the slope of that line, there has to be somewhere, and we don't know where it is yet, but there has to be somewhere that if I draw a tangent line, it has the exact same slope as that secant line. And why that's guaranteed to occur is because anywhere between -1 and +3, this function is both continuous and differentiable the entire time. So first off, we need to find the slope of the secant line on the interval from -1 to 3. Well, that slope, hopefully you can see, we would just go y2 minus y1 over x2 minus x1. That gives me 8 over 4, which gives me a slope of 2. So that's the first thing here, looking at this. This has a slope of 2, this secant line that I just drew. Okay, so now we're going to say, okay, well, I'm going to take the derivative of this function. You might be saying, why are we going to take the derivative of the function if I just found the slope of the secant line to be 2? Well, what the mean value theorem says is it says, now that we know the function is continuous and differentiable between x equals -1 and x equals +3, there has to be somewhere that the slope of the tangent line is going to be identical as the slope of the secant line. And the slope of the tangent line is always found by taking the derivative and plugging in an x value. So what we do is once we have each of those things individually, the derivative and the slope of the secant line, we set them equal to each other to find out the x value at which this is actually going to occur. The x value where the tangent line slope and the secant line slope are going to be exactly the same. Okay? So every once in a while what happens is you might get a number that is outside of your interval. All that's saying is that still is true. The slope of the tangent line still is true at that point, but it's not on the interval, so the mean value theorem that we're looking at for this particular instance does not apply there. Okay? So, again, what's happening here? We've got those 2 points. I connect them together to make my secant line. And then we just found at x equals 2, so x equals 2 is right there. If I were to draw, oops, yeah, that's right. Didn't I get, no, I got 1. Sorry. At x equals 1, if I were to draw a tangent line, those 2 lines would be parallel to each other, which I know doesn't seem like a big deal. You're like, okay, so what? But it is a really big deal for some stuff we talk about later. Okay? So if you want 3 steps to using the mean value theorem, step number 1, look at the interval in question, and then on that interval, decide if there are any discontinuities or corners or cusps. If there are, then we just say we can't use the mean value theorem here and we're done. But as long as it's continuous and differentiable, what we do is find the slope of the secant line from the endpoints of the interval, and then take the derivative of the function in question. Then lastly, what we do is we set the derivative equal to that slope, and we solve for x. Once we have the solutions, we just have to say, okay, is that number between the 2 x values that we are interested in to make our interval? Now, what will happen on the AP test is they'll say, okay, I'm looking between x equals -2 on a function and x equals +4, and I'm going to tell you right now that the slope between those 2 lines is 1/3. Can I use the mean value theorem to say there must be somewhere that if I draw a tangent line, it's going to have that same slope? And the answer in this case is no. We cannot say that because I have 2 discontinuities on the interval in question. And that's all you have to say. Once you say there's a discontinuity, the mean value theorem no longer applies, so we don't have to worry about it. So like from 7 to 9, if I were to connect these 2 points from 7 to 9, I can see that they have a slope of 0. There's no discontinuity, but at x equals 8, we have a corner, which makes our function not be differentiable. So again, I cannot apply the mean value theorem. Now, if I were to look at the same graph, but look between 2 different points, between the points 0 and 2, whoops, and I were to say, can I use the mean value theorem there if the slope between those 2 points, if the slope between those 2 points is 3/2? And the answer this time is yes, I can, because this function is both continuous and differentiable between those 2 x values. So hopefully the mean value theorem kind of makes sense. It's not something that's like of the utmost importance for you to like understand how to do every problem, because it doesn't show up out very often on the AP test. But it is an idea that appears an awful lot that we need to be able to know how to apply. So if you have any questions about this or anything else, please come on in and we can answer those.